everybody, this is final presentation of Fourier optics. In this presentation, I'm gonna talk about two problems of chapter 4 from Goodman's book. First of all, I will talk about problem number 10, but before explaining this problem, I will tell you a brief description of Fraunhofer diffraction. It refers to diffraction pattern in an area that is commonly known as the far field. Fraunhofer diffraction is a powerful tool, can be used in many applications, such as laser beam propagation, image analysis, and spectroscopy. Let's go to problem number 10. In this problem, we have to find an expression for the intensity distribution in the Fraunhofer diffraction pattern of the aperture results shown in right side. First of all, I will show you the numerical solution, then go to simulation. But for first step, it's better to know about a circular aperture. Let the radius of the aperture be W. Q is a radius coordinate in the plane of the aperture. The circular symmetry of the aperture suggests that the Fourier transform be written as a Fourier-Bessel transform. R is the radius coordinate in the observation plane, rho radius in the spatial frequency domain. The field transmitted by the aperture is equal to the amplitude transmitted. So the intensity distribution can be written by IR, and the diffraction pattern of the circular aperture is like this figure. For our case, it includes interference term with Bessel function shape. In this problem, the central structure is bounded by a circular aperture of radius 2W. The amplitude transmittance function for this aperture is given by TA. The Fourier-Bessel transform of this function is like this relation, and then the intensity is given by this equation. Note that some of the incident light is absorbed, and in addition the sinusoidal transmittance variation across the aperture has deflected some of the energy out of the central diffraction pattern into additional side patterns. The central diffraction pattern is called the zero order of the Fraunhofer pattern. Let's go to MATLAB code to display the irradiance pattern of this problem. First of all, I will define some parameter, then ky space, xy space, and k. Then go to side length, propagation distance, and at the end irradiance and irradiance image. By running the script, the results will be shown in next page. Let's take a look at this video. As you can see, by changing the radius of central pattern, diffraction pattern, and Bessel function shape will change. Consider that Bessel beam are a special type of light propagation that does not diffract it. Let's go to another problem. Problem number 20. A certain circularly symmetric object, infinite in extent, has amplitude transmittance is given by this relation. In this relation, which J0 is a Bessel function of the first kind, zero order, and R is a radius in the two-dimensional plane. This object is illuminated by normally incident unit amplitude plane wave paraxial conditions are assumed to hold. At what distance behind this object will we find a field distribution that is of the same form as the object? Okay, go to mathematical solution. The solution begins by first finding the special frequency spectrum of the field transmitted by the structure. The Fourier transform of each of the two components of the object is given by these two relations. Since the transfer function for free space propagation under paraxial condition is given by h rho, which is equal exponential jkz times exponential minus j pi lambda z rho square. After propagation over distance z, the field will be given by ur, or which can be simplified to the second relation. For imaging to occur, we requiring that 3 pi lambda c equal to k pi, where k is an integer, thus image will appear at distance given by z equal to k over 3 lambda. Z give us the distance which image will appear behind the object. So for finding the field behind the object, we wrote MATLAB code. First of all, we define some parameters which was mentioned in problem. Then wave number domain, and we define some parameter and limitation for coordinate. Then go to transfer function, which was shown with h, and at the end we define the field behind the object. The results will be like this. Let's take a look at this video. The left side is the original image, and we see that the image behind the object in different distance will be like this shape. Okay, I will show you the image behind the object at different distance. Okay, in this chapter, we learn how to deal with different kinds of diffraction, Fresnel diffraction and Fraunhofer diffraction. Thank you so much for listening.